Okay, so I'm going to review Gauss's law, basically all of Gauss's law, like every example you might see. So first of all, Gauss's law is the statement that the electric flux, this right here on the left-hand side is the electric flux, that the electric flux through any closed surface, that's what the circle's all about, is equal to the charge inside that closed surface divided by epsilon naught. So what does this mean? It means you've got some electric field, so there's some charge somewhere creating an electric field. So if you make a Gaussian surface, that's what this A is. It's got to be closed up. So this blue dashed line in here, everywhere in these examples going forward, these dashed lines will represent the Gaussian surface. It's an area. It's got to be closed up. It's got to include all of this area. There's got to be a defined inside and outside to this area. So integrate the electric field that pierces through that area. So if you do this, if you integrate the electric field that pierces through that area, you're finding the electric flux, and that will always equal the charge inside. So the charge inside that Gaussian surface divided by epsilon naught. There may be charge outside. So in these pictures, this tan is charge, but it's charge that's not inside your Gaussian surface as drawn. So it's only the charge inside that counts. And this flux will always equal Q over epsilon naught. However, this is only useful if you can take this electric field and put it outside of your integral. And how do you do that? You do that by picking an area, a Gaussian surface, such that the electric field is uniform across the area. So pick a surface such that that electric field is just constant along that area. And then it's constant in the integral as you're integrating through space. You bring it outside, and then you just have E times the integral of dA, but the integral of dA is just A. So you get E times A equals Qn over epsilon naught. So if you're using Gauss's law to like find something, you're going to be using this form right here. You're not going to be using it in this form. You start with this form, but you immediately turn it into this form. And there's a bunch of examples. So let's see what those look like. So there's really only three cases. You need to bring the E out. So there's got to be a symmetry. So you're going to have spherical symmetry, cylindrical symmetry, or planar symmetry. So the simplest case is obviously just a point charge. What do? You create a Gaussian surface that's a sphere. So this looks like a circle, but it's a sphere. It's a 3D, sphere. The surface is 2D. It's the 2D surface of the sphere. So you do E, you bring the E out, turns into E times integral dA. dA is just the area of this sphere. So my Gaussian surfaces are always going to have radii of little r. So E times 4 pi r squared is the surface area of a sphere. And if you notice, this left-hand side for all these examples are all going to be identical. They're all E times 4 pi r squared because that's the surface area of the sphere. And if it's spherical symmetry, that's all you get to choose. So the left-hand side's fixed. The only question is, what's the right-hand side become? Well, for a point charge, it's easy. How much charge did you enclose with this sphere? Just Q, and then you divide both sides by 4 pi r squared here, and you get E would be the normal 1 over 4 pi epsilon naught, which is also known as K, the electric constant, Q over epsilon naught, just the normal formula for the electric field from a point charge. So I'm not going to go ahead and divide through each time. Dividing through is easy. Divide by 4 pi r squared and you get what E is. I'm just going to show you how you would set it up. So that's the point charge. What if you had a point charge inside of an uncharged metal shell? This looks like a tube, but it's a shell. You got to imagine this gray as like a spherical shell. I'm just cutting it through the middle and we're seeing what the inside looks like. But this gray is a sealed up shell of metal. So what if you're inside of A? Well, your Gaussian surface would look like this. It's a 4 pi r squared, that's the area. R would be less than A. And how much charge do you enclose? Just Q, that's it. Okay, so what if you're out here in the guts of the metal? You might be like, oh, I still enclose Q, right? No, because what's going to happen is this charge Q is going to attract a negative amount of charge equal and opposite to what it is. So there's going to be a negative Q on the inside edge of this metal. So the metal allows, electrons to move throughout it. If you've got positive Q on the inside, negative Q comes in to negate that positive Q, and you're enclosing a total charge here of 0. So inside of a metal, the electric field's 0. That's always the case for electrostatics. If the charges are done moving, they're not moving anymore, they figured out where they want to be and they're staying there, then the electric field in a metal is 0. What does that mean for the outside? Well, you're going to have plus Q on the outside. So this charge, or this metal, was uncharged to start. So if negative Q ended up on the inside edge, attracted by this positive Q, then you've got to have positive Q on the outside edge because this metal had no, charge total. So its charge just got polarized. Negative went this way, positive went that way. The metal is still overall uncharged because it has a negative and positive. So when you're out here, when your Gaussian surface is larger with a radius larger than B, well, positive Q, and positive Q just adds up to positive Q. These just cancel out. The metal just serves no purpose now in terms of the outside edge, and so the charge enclosed is just Q. So it looks like this. What if the metal was pre-charged? This used to freak me out. I was like, what? What if it already started with a charge Q? The metal does. All right, well, if you're inside, no big deal. If you're inside, you're still enclosing just Q. So if R is less than A, Q. If you're inside the metal, you might be like, oh, it's going to be different now. No. If you're in a metal, the electric field is 0 for electrostatics. It just doesn't matter. Tell me electrostatics in a metal, I could just tell you 0 electric field. So what happens if you're out here, though? So what's happening in the guts of this metal is that Q is still going to attract negative Q on the inside edge, even if this metal was already charged. So just like before, it's negative Q on the inside edge. But what that means is that the outside edge, because this metal has to have a total charge Q, you need to make sure that the outside edge plus the inside edge adds up to Q this time. So instead of having positive just Q on the outside edge, you're going to have capital Q plus lowercase q, because if you add all the charge together, this outside edge plus the inside edge, negative Q and little q cancel, and you just get positive Q total. So you need to make sure outside edge plus inside edge adds up to the total amount of charge on the metal shell, and this inside edge is always going to equal whatever's in here. So if you had a charge little q inside, you got to have a charge little q plastered from the metal on this inside edge. So this is little negative q regardless of what you make that. It's just the outside edge that'll change. And why does the charge all go to the edge? Because they repel, They're trying to get far away from each other as possible. So you go to the edge. So the leftover goes over here to the edge. So when you're outside here, Gaussian surface outside here, you're enclosing little q plus negative little q plus capital Q plus little q. Well, little q and negative q cancel, so you get q plus q total enclosed out here. What if you had a metal shell but there was no charge inside? Well, this time, inside here, less than A, you got no charge in there. What if you're in a metal? 0, always 0. Inside a metal, 0. What if you're outside here? Okay, well, the metal shell had a charge Q, so you're enclosing Q. Not that bad. Okay, so what if it's an insulating charge sphere? It's insulating means you can have charge throughout the guts of it. So this is supposed to represent a sphere with constant charge density, uniform charge density. What's this dark orange mean? This dark orange is inside my Gaussian surface that I've drawn. So if you're inside of here with a radius less than capital R, the way you find your Q is that, rho, the charge density is the charge per volume. So that means charge is just the charge density times volume. What volume? Volume of a sphere, because we had a sphere here. And it's little r. Little r is the radius of my Gaussian sphere. Just like this is little r, that's little r if my radii is less than capital R. What happens if I'm out here, if my Gaussian surface is bigger? So say I want to know the electric field out here, so I put my Gaussian surface all the way out here with a radii greater than capital R. Well, you got to stop your, you multiply by capital R here. The most charge you can have is all of the charge, and all of the charge is the charge density times all of the volume. You can't keep acting like you're going to add charge out here by moving further out. The most charge you get is all the charge, and all the charge stops at capital R. So you have to stop at capital R. So now you'd have a capital R here and a little r here. Little r being your variable where you're finding the field. Capital R just being the radii of this charge density sphere. What if they didn't give you charge density? What if they gave you just total charge in the sphere? You do it the exact same way. It's just you have to craft your own charge density. So they didn't give you rho. What do? You make your own rho. You say, if I take total charge divided by 4/3 pi. Oh, here's a question. Is it little r or big R? You've got to put big R. Look, if I put total charge, that's supposed to be cute. If I put total charge here, I need total volume. So if I really want the charge density, it's total charge over total volume. I could put charge in here divided by volume in there, but I don't know the charge in there. That's the whole point. I want to find the charge in here. I don't know what the charge is in this Gaussian surface here. So if I'm inside, I want to make a charge density. All I know is the total charge, so I divide by the total volume. That's my charge density. That's right here. That's rho. So that's rho. What do we multiply? The same thing we did by before. You multiply by the volume you're finding. So if I'm in here, if my Gaussian surface is less than, has a radii less than capital R, I'm only enclosing this much charge, so I multiply that much volume. This whole numerator gives me the volume, gives me the total charge in this volume right here. What if your Gaussian surface is out here? You want to find the electric field out here. Left-hand side's still the same, but now you're enclosing just total Q. So you just plug in total Q. You might be like, wait, can't I do the same move where I plug in capital R now out here because I'm far out? Yeah, but look, it's just going to cancel, and you just get capital Q. So same deal. What happens if there's a hole in your insulating charged sphere? Sometimes you call this a shell, like if it's got a hole in the middle. And this is a sphere, not a tube. So it's a sphere, not cylindrical. If you're given the charge density, well, if you're inside here, you're enclosing no charge, so zero charge. If you're in here with a radii greater than A but less than B, you do it the same as before, charge density times this here would be the volume of this total sphere, but you have to subtract out the hole. So you subtract this hole, and the hole has a volume of 4/3 pi little a cubed. So in other words, the volume of this portion right here of the charge, where the charge is, which is what we want. You multiply by the charge density by that volume, because charge density is charge per volume, so charge is density times volume. You need to multiply it by the volume where the charge is. You don't get to multiply by the volume where the charge isn't. That won't give you how much charge there is. So you subtract out the whole. So what this here is giving is the total total volume of this region here, between the blue line and this black line. Got to subtract out the whole, multiply by charge density, and that gives you your charge, and that's the charge enclosed. What if you were out here with a R greater than B? Stop your multiplication at little b. You can't get any more charge than the total charge. So what this represents is the total volume. Total volume meaning the entire volume of this shell. So multiply the charge density by this total volume, and you'd get the total charge enclosed, which is all the charge. You should not have a little r here, because little r is not going to be adding any charge out here. I can't be acting like charge gets any bigger once I go past the outside edge of this. So this remains little r, but this one does not. What happens if they gave you Q naught instead? Again, you just craft your own charge density. This one's going to be a little ugly. You'd be like, okay, well, charge density is the total charge over the total volume, but it's like, crap, what's the total volume? It's this mess. Remember, this is what we just wrote a minute ago. 4/3 pi b cubed would be the entire volume of the sphere minus the whole. That's what this is. This is, I'm going to write it as v total. It's this denominator right here. So this entire term here is the charge density. You just had to make your own. And then you multiply what you need to multiply by. Obviously, if you're inside A, there's no charge. If you're in the guts of this thing, this is not a metal, so it's not zero. It's insulating. If you're in the guts of this thing, you multiply by the same thing we had before. So this is the exact same expression, except we had rho here. Now we have to make our own rho. So rho is total charge over total volume. Now you just multiply by the volume where you had charge. This gives you the charge enclosed by the Gaussian surface if the radii of the Gaussian surface is less than, capital B, but greater than A. So this is just the volume enclosed. This is the total volume and total charge, which is charge density. And then if you're outside the whole thing, it's kind of easy. You're enclosing the total charge. So there you go. And again, you're like, can I just put B here? You can, but these whole things would cancel. And you just get Q naught. What happens if your charge density is not uniform? Well, then you got to do an integral. So the idea is you're like, okay, crap. The total charge is the charge density, or the charge enclosed would be the charge density times the volume, but what if my charge density is not constant or uniform? Well, you could say the little bit of charge within any little chunk, you know what I mean? In that little chunk, if you make it infinitesimally small, an infinitesimally small volume, well, the charge density can't vary in there because there's no time for it to vary. There's no space for it to vary if it's infinitesimally small. So Rho has some well-defined value at that point. And now we can just integrate both sides, and I can say that my Q is going to be the integral of rho dV. This is always true. It's just a matter of like, what would you put in for dV? So this is what I'm doing up here. I'm saying, okay, Q enclosed. This whole numerator is Q enclosed. I'm taking integral rho dV. Why is this dV? Because look, dV of a sphere, the way you can figure it out, write down the volume of a sphere. V of a sphere is 4/3 pi r cubed. Now take a differential of that. What's going to happen? The 3 is going to come down. It's going to cancel out the other 3. You're going to end up with 4 pi r squared and then dr. You can imagine doing this as a derivative. dV over dr. You know, dV over dr. If this is the volume right here, 4/3 pi r cubed is going to be, the 3 comes down, you get 4 pi r squared. And then just move the dr over and you get the dV is 4 pi r squared dr. So this is dV for the spherical case. Now, it's only true if it's got spherical symmetry. That is to say that changing this angle isn't going to change the charge density. And changing this azimuthal angle doesn't change the charge density. So this is dV if the only variation that's occurring is in radius. So the only variable that the charge density depends on is radius, like how far out you're going, which is almost always what the case is. If you wanted to do it with these angle ones, you got to write a nasty dV in here, and I doubt that's going to be on the AP test or any introductory class. So this is your integral rho dV. What do you integrate from? From 0 in this case, because there was charge from here, all the way to little r. So you go from 0 to little r, that gives you the charge inside here, and you integrate this. So this is little r, that contributes. You can't pull that out. You can pull the 4 out, you can pull the pi out, but the r, little r stays in there. And you'd be given rho. Maybe rho is like kr squared, or maybe it's like k over r, who knows? Probably not k over r if you're going all the way to 0, but what if your r is greater than big R? Just stop your integral there, you know, just integrate all the way to the edge. That's it. You got all of it. Don't go any farther than that, and that's your total charge in there. This is also an expression for the total charge in your sphere. Integrate rho through the entire volume, you get the Q total, in other words. What would happen if you had a hole in your sphere? This time it's a shell. Well, obviously, if you're in here, you're going to have 0 because you're enclosing 0 charge. What would happen if you're in the guts of this thing? It's not a metal, so you can't say it's 0. You do the exact same integral you did before, integral rho dV, but just integrate from A. You know what I mean? Don't start at 0. Integrate from A to little r. That's where you got to integrate from to get the volume, or to get the charge in here. And then what if you're outside the whole thing? Well, you integrate from A to B. That includes, you know, the whole thing. So you go from A all the way to B. That gives you your total charge enclosed. This again would be an expression for the total charge in this system. And of course, okay, you divide both sides by 4 pi r squared. That gives you E. Typically, you're trying to find E in these cases. So those are almost all the spherical cases you could expect. What happens if it's cylindrical? Well, same idea. You do E times A, but this time the area of a cylinder is 2 pi r, because that's the, you know, circumference here, times height gives you this area here. And you might be like, shouldn't we add pi r squared plus pi r squared? No, because look at the electric field is going to be pointing this way. So the electric field pierces this area here, but you know, there's no flux if the electric field doesn't pierce your area. So if this is running along the surface, it's not actually piercing that area. So these end caps don't actually matter toward Gauss's law. Yes, they have an area, but there's no electric flux through them. The flux is only through this, like, you know, toilet paper roll part, not the end cap part. So the only part of the area you have to include in here is this roll part, which is 2 pi r, you know, length times height gives you the area of this thing. So that's your area. This is going to be the same area for every single cylindrical problem, always 2 pi little r h. This is my Gaussian surface. What if I had a line of charge? And let's say the charge was lambda. What does lambda mean? Lambda is the amount of charge per length instead of charge per volume. So it has units of coulombs per meter. Well, how do you find the charge? Charge is going to be lambda times length. So how much charge would I enclose here? Well, it's like all of this charge. How much is that? Lambda times the length of it, but I called my length of the cylinder h. So it's lambda times h. The h would cancel h. You'd move the 2 pi over and you'd get what you'd get. So this would be the amount of charge enclosed. This has to be an infinitely long charge density so that you can say the E always points straight out and you never get any of these weird edge effects. So that's the easiest one. Lambda times L gives you the charge enclosed. What if it's an insulating cylinder? Shoot, you know how to deal with this. Rho is charge per volume, so that means charge is rho times volume. What's the volume inside of this Gaussian surface? Remember, the left-hand side is the same. Here's my Gaussian surface, 2 pi RH is the area, but I need to multiply by volume to get my charge in here. What's the volume of a cylinder? It's just pi r squared, area of the end cap, times h. So the length of this cylinder. So this is the area. And that's if I'm inside, if my Gaussian surface has a radius less than capital R. What if my Gaussian surface has a radius greater than capital R? I draw a Gaussian surface like this. Well, obviously I have to stop my charge at the end. Like there's no more charge than the total charge. So if I'm way out there, I multiply by pi big R squared times h. This would be the total volume. This would give you the total charge, even though on the left-hand side here, I'm still little r. Little r is the radii of the Gaussian surface. And this is the r you use to find the charge inside. So these do not have to be the same. And then you divide by 2 pi RH. Again, the h cancels. The h is basically always going to cancel here. And you get whatever you're going to get. What happens if it's non-uniform? You guys know how to do this now. You say like Q is the integral of rho dV, just like we got over here, except dV for a cylinder isn't going to be 4 pi r squared dr. You know, this is the area of a cylinder, or sorry, the volume of a cylinder, pi r squared h. So if you take a differential of that, the 2 comes down, you get 2 pi r, and then there's a dr. Again, write it like a derivative if you want, and then move the dr over. You get this. This is the dV of a cylindrical symmetry, again, assuming there's no angular dependence here. The only variation happens because of the radius. But that's basically every problem you're going to meet. So you integrate rho dV for a cylinder. If your radii, if you want to know the electric field inside here, your radii is going to be less than capital R. So you go from 0 to R to get the charge enclosed in this Gaussian surface here. What if you're outside the whole thing? You got to include all the charge, which means you just stop integrating at the edge, because at the edge, that's including all the charge here. So you stop there. This here with the integral would be an expression for the total charge in this Gaussian cylinder of height h. And the h's would end up canceling again. So what would happen if there was a hole inside? Easy, just like, you know, well, there's no integral here. If your rho is just uniform, okay, fine, have rho times, same deal, total volume, but subtract out the hole. This right here is just an expression for the volume of the hole. So just subtract out that hole, and you get what the answer is. And if you're out here, if your Gaussian surface is out here, fine, just only go to b squared, right? You can't have any more charge than the total charge, and then you still subtract out the hole. So you don't have any of that volume there. So you want to make sure that you're only including charge where there is charge. So if you're multiplying rho by a volume, make sure you're only multiplying by the volume where the charge is actually present. You don't get to multiply by the volume of a hole. That's why we have to subtract it out. And if it was a charge density, this one's almost easier. Just integrate from the inner radius to the wherever you're at. So if there's a hole, just don't start at 0. Don't start at 0, start at A and go out to R. Or if you're way out here, if you're outside the Gaussian, or if you're outside the charge, that is to say, if your Gaussian surface is outside the charge density entirely, just go from A, not from 0, from A to B. And this would be an expression for the total charge of the cylinder. Okay, whew, last one, here we go. That was cylindrical. The last possibility really is just planar symmetry, and this one's almost the easiest. So say you have an infinite plane. The electric field is just going to be pointing straight out of there, up on the top, assuming it's positive, and down on the bottom, because field points away from a positive charge. What would Gauss's law look like? You draw something. It doesn't have to be a square. It could be like it could be another little cylinder, but it's got to be oriented like up to down, right through this plane. And since your electric field points this way and that way, you're going to get electric flux through the top face and the bottom face. You get none through the sides. So this electric field, running right along the sides. It doesn't actually pierce it. So the only contribution to the flux is around the top face, is through the top face and the bottom face. But there's two of them. That's why I have 2A here. Whatever your area was of the top one and the bottom one, that's what your Gauss's flux is going to be. Now, you might be like, what do I write as the area? Is it height times width? It doesn't matter, because watch. the total charge enclosed by this. It's got to be closed up. So the sides don't matter in terms of like the flux, but you have to imagine it because the sides matter in terms of finding out how much charge is enclosed. Because the only charges enclosed would be this little shadow amount that's within this imaginary box. How much charge is that? Well, the surface charge density is just charge per area. So charge would be surface charge density times area. And surface charge density times area is how much charge you've got enclosed there. You might be like, how come it's not times 2? Well, because there's only one of these. You only enclosed one of these. The electric field is piercing 2 areas for the flux, but the amount of charge that's in there is only one of these. It's not like there's 2 planes or something like that. You could have 2 planes, but in this case, there's only 1 plane. So the total charge you're enclosing is just sigma times A, and this is your flux. So the A would end up canceling. This is why I said it doesn't matter. Write it as pi r squared. If you make this a circle, write it as height times width. It doesn't really matter. That just cancels out. You get E would be sigma over 2 epsilon naught. This is the freakiest result of all Gauss's law because it says that the electric field outside of this surface doesn't vary with distance. Get as far away from this infinite plane as you want, and the electric field is constant, uniform up here. It doesn't die off at all. It's just weird. So the graph of this thing, they're like, what's E as a function of R away from this, call this R or something. It's just a constant value. It just freaks me out. But, it's an infinite plane. How do you make that? You can't. We're just playing pretend land right now. So if your plane is really big compared to the distance you are away from it, this would be an approximate value, but you're never going to meet an infinite plane out there except for the AP exam. But now you're ready. That's the one. But it's uniform, so if you had more, you could just literally add these contributions up once you know the value from one. It doesn't matter how far away it is. Just make sure you know which way the fields go. If they go opposite, they cancel. If they go in the same direction, they add up. You'd have 2 times this. Okay, so just a quick recap here. What you put in this right-hand side is either like a Q, or you multiply a rho times a volume, or you might have to integrate rho dV. If it's spherical, you're going to be like, okay, integral rho dV for spherical was 4 pi r squared dr. That was for spherical. Or for cylindrical, you do integral rho, let's see, what was it, 2 pi r h dr. This would have been dV for the cylindrical case, and this was dV for the spherical case. How do you figure those out? Remember, just write down the volume. Would be pi r squared h. Take a derivative of both sides, dV dr, and then d this dr. The 2 would come down, you get 2 pi r h, and then move the dr over, and you get what dV is. Okay, so that is all of Gauss's law in a nutshell. Basically every example you might ever see. I'm going to link this document in the video for convenience's sake. Good luck.